Hey everyone, so we made it to our last calculus video for the year. Well, we might have some review videos for you, but the last one for chapter 10 at least, which means the last one where there's anything new. And the nice thing about it is that because we pretty much have taught you everything you need to know already, there's not really anything new in this one either. So what we're going to be doing in this is just going through a couple of FRQs so that you can see what area and volume problems might look like on the AP test. So for the first one, we can use our graphing calculator, so make sure you have that. For the second one, it'll be a no calculator question. So let's take a look here. We can see we've got this table, all right? A tank has a height of 10 feet. The area of the horizontal cross sections of the tank at height h feet is given by the function a, where a of h is measured in square feet. So what that means is we're given the height in feet, and we're given the area of these horizontal cross sections of the tank. All right, so what you have to imagine is we're taking these areas and dividing it into cross sections to find the area, and then we were revolving that to find the volume. So what we're looking at here then is they already gave us the areas of the cross sections, which is kind of nice. A is continuous and decreases as h increases, so that's going to be important. Selected values of A of h are in the given table. All right, so use a left Riemann sum with 3 subintervals to approximate the volume of the tank. Indicate the units of measure. So again, what we did is we took areas of these cross sections and we added them all up to find the volume. And we know that we do that with an integral. But since we don't have a function for this, we have to use a left Riemann sum to just approximate it. So let's go ahead and see what this is going to look like. We have 3 subintervals, so we're going to go from 0 to 2, 2 to 5, and 5 to 10. And we're doing a left Riemann sum. So let's see, at 0, the height is 50.3, or I'm sorry, the area, excuse me, and then 14.4, and then 6.5. So that means this volume is approximately, since we're doing rectangles, we know it's base times height, so it's 2 times 50.3 plus 3 times 14.4 plus 5 times 6.5. And since this is a calculator question, we can go ahead and use our calculators to just do that. So 2 times 50.3, 3 times 14.4, 6.5, and we get 176.3. So now we need to think about what the units are here. So keep in mind, we're finding an area of a rectangle, so it's base times height. We know that this distance here is the height, so that's measured in feet. And we know that all the heights of our rectangles were these areas, which are in feet squared. So when we multiply those, we end up getting feet cubed, which should make sense because we're finding a volume. But it's always good to check and make sure that the stuff you have makes sense. All right, so does the approximation in part A overestimate or underestimate the volume of this tank? Explain your reasoning. Well, we had to use a Riemann sum, because we didn't know the actual function. But they did tell us that A is continuous and decreases, which means it kind of does something like this. All right, so if we have a decreasing function and we draw in some rectangles with a left Riemann sum, that's going to be here to here, and then here to here. And we can clearly see by looking at this then that if the function is decreasing and we use a left Riemann sum, that's an overestimate, sorry. So the approximation is an overestimate because A is decreasing and a left Riemann sum is used. So we've talked about this before in some other examples that we've done, but this is not something that I memorize. I always just draw myself a quick sketch of what's going on. So it's a decreasing function, we've got a left Riemann sum, and then I can see whether it's an over or underestimate. Don't try to memorize that, okay? All right, let's move on to part C. So the area in square feet of the horizontal cross sections at height h is modeled by the function f, given by this right here. Based on this model, find the volume of the tank, indicate the units measured. So this is really similar to part A, except instead of using the information in table A, or in the table up there, excuse me, we were actually given the function. So we know if we have the area of these cross sections, we can take the integral to add all those areas up and get the volume. So we know that the volume is going to equal the integral. We're starting at 0. And the height of the actual tank is 10 feet. So we're going from 0 to 10, and we're going to integrate f of h dh. So again, since this is a calculator question, we can just go ahead and do that. So math 9 from 0 to 10, and then our function is 50.3 e to the 0.2x plus x. We're integrating with respect to x. And remember, we want 3 decimal places, so we're going to do 101. This is approximately 101.325. And we need to think about our units. So again, we're doing volume, so we get those cubic feet again. Now I want to take a second and point out to you, 101 is less than the 176 that we found in part A. We said in part B that part A should be an overestimate, so we know that we're right then. We can kind of, use the answers that we have to make sure we're on the right track there. So don't get too bogged down in doing each part separately. Remember that they are all connected to each other. All right, on to part D. So water is pumped into the tank when the height of the water is 5 feet. The height is increasing at a rate of 0.26 foot per minute. Using the model from part C, so using this function f of h, find the rate at which the volume of the water is changing with respect to time when the height of the water is 5 feet. Indicate the units of measure. All right, well, hopefully what jumps out at you in this problem is we need to find the rate at which the volume of the water is changing with respect to time. That right there, especially the part about the rate changing with respect to time, should tell you that we need to start thinking again about related rates. I know it's been a while since we've done that, but hopefully that jumps out at you. So if we're going to tackle this problem, it means we need some type of an equation that relates, right, a related rate, the rate of the volume, and then the height. So if we think back to part C, we said that the volume is equal to the integral of the areas of the cross sections. So we're going to start out by writing this integral. The volume is going to equal the integral from 0 to h. We're going to say h because h is going to be the height of our, the height of the water in the tank. So from 0 to h of, instead of f of h, I'm going to put f of x dx. So remember, we can't have h in all of these places. So since we're going to use h to stand for the height of the water, we're going to integrate from 0 to h. This right here is an equation that relates the volume with the height of the actual water, okay? So if we're going to do a related rates problem, we know that that means we need to take a derivative because I want the rate at which the volume is changing with respect to time. So that means if I take my derivative, I'm going to have dv dt, and then this is where the fundamental theorem of calculus comes in. I'm taking the derivative of an integral. So I'm going to take that h and end up plugging it in, right? F of h. Now we have to be careful because we're differentiating with respect to t, and this is an h. This is where implicit differentiation comes in, and we need a dH dt. We need the rate at which the height is changing with respect to time as well. So this is now our formula. So let's think about what we have and what we actually need. So in this equation here, we have a dV dt, we have h, and we have dH dt. So if we look, we know that we want to find the rate at which the volume of the water is changing when the height of the water is 5 feet, so h is 5 feet. And we were given that the height is increasing at a rate of 0.26 foot per minute. Well, since it's increasing, that's a positive value, so this is 0.26. And then we're looking for the rate at which the volume is changing, so dV dt is what we're looking for. So really, what we're going to do is we are going to evaluate dV dt at h equals 5. So we're going to have f of 5 times dH dt, which is that 0.26. And so we can put that in our calculator. So if I want to do f of 5, it means I'm going to plug 5 into this right here. Times 5 plus 5, and then multiply the whole thing by 0.26 because that was my dH dt. All right, and then 3 decimal places, so we get 1.694. And then remember, we want to think about the units here. So since this is the rate at which the volume is changing, we know that it's cubic feet per minute. And there we go. Okay, moving on to question 2. So let R be the region bound by the x-axis, the graph of y equals the square root of x, and the line x equals 4. So find the area of region R. So the first thing we need to do then is draw a picture of what's going on. So hopefully you guys are getting to be pros at drawing the square root of x because we've done it a lot lately. So we're here, here, and here. And then we have the line x equals 4, which is this vertical line right here. So we can see that the top of this region stays the same the whole time, which means I can find the area, and I'm going to be doing it with respect to x. All right, so that means that I'm going to be doing top minus bottom. So the area that's enclosed there is the integral from 0 to 4, because those are my x values, of the top, which is the square root of x, minus the bottom, which is 0, and then dx. So really that's the integral from 0 to 4 of the square root of x dx. And this is a no calculator question, which means we're going to have to do this antiderivative by hand. We know that the square root of x is really x to the 1/2 power, which means if I add 1, that's going to become x to the 3/2. And I need to multiply by the reciprocal. So I have 2/3 x to the 3/2 plus c, and I'm going to evaluate it from 0 to 4. So if I plug in 4, let's see, 4 to the 3/2. So the square root of 4 is 2. 2 cubed is 8, times 2/3 gives me 16/3. Plus c, minus, if I plug in 0, I would end up getting 0, plus c, and I know the c's will end up canceling, so I get that the area of that region is 16/3. Part B is something that's a little different. So it says the vertical line x equals h divides R into 2 regions with equal areas. Write, but do not solve, an equation involving integral expressions whose solution gives the value of h. So really what we want to imagine is we want to be able to draw some vertical line in here between 0 and 4 that's going to cut this area in half. So I don't really know where it is, but I'm just going to pretend that it's right here. And I'm going to write x equals h. So we're imagining that that orange line there is cutting this area in half. So we have two ways that we could actually write our answer to this. So the first one is we could say that the integral from 0 to h, whatever h is, of our region, which is the square root of x dx, is equal to half of this area. Well, the whole area is 16/3, so half of it is going to be 8/3. All right, so that's one way that we could write an answer for this. So this is telling us that the integral from 0 to h of the square root of x dx is half of the area we found in part A. All right, the other way that we could write it is we could say that the integral from 0 to h of the square root of x dx is equal to the integral from h to 4 of the square root of x dx. So again, we're just saying if we go from 0 to h and from h to 4, those two areas are equal to each other. You do not have to write both of these on the AP exam, but I want you to recognize that both of them are valid options, okay? For part C, it says find the volume of the solid generated when R is revolved around the x-axis. So let's quickly draw ourselves that picture again so that we can see what we're revolving here. 1, 2, 3, 4. So here's my square root of x. Here's the line x equals 4. And we want to revolve it around the x-axis. And so if we imagine taking this area in here and revolving it, there's not going to be any holes. And so I'm going to draw in my area here. My cross sections will be perpendicular to the x-axis. So that means that whatever this is right here is going to be the radius. So since I'm going to do this with respect to x, the radius is going to be top minus bottom. And since there's no hole, I don't have to worry about having more than one radius because there's no hole in the middle to subtract out. So remember, top minus bottom, so we're going to do the square root of x minus 0. Oops, minus 0. And so the radius is really just equal to the square root of x. And the areas that we're finding here are all circles, so they're all going to have pi r squared. So the volume is going to be pi times the integral from 0 to 4 of my radius squared, so the square root of x squared, dx. So this is really pi times the integral from 0 to 4 of x dx. And now all we have to do is take the antiderivative. So I'm going to rewrite it down here. Pi, the antiderivative there would be x squared over 2 plus c, and we're evaluating from 0 to 4. So pi, if I plug in 4, 4 squared is 16, divided by 2 is 8, plus c, minus, if I plug in 0, I'd have 0, plus c. The c's end up canceling out, and so we get that the area here is going to be 8 pi. All right, one more question. Sorry, I know this is getting a little long. I was hoping it was going to be quicker. The vertical line x equals k divides the region R into two regions such that when the two regions are revolved about the x-axis, they generate solids with equal volumes. So this is really similar to part B, except instead of dividing the area in half, we're dividing this volume in half. So again, we're imagining some random vertical line here. That's x equals k, which is dividing our volume in half. So very similarly to part B, we have two different ways to do this. We can say that pi times the integral from 0 to k of the square root of x squared dx is equal to half the volume we found. So it was 8 pi, so half of that would be 4 pi. So this is one way that we could say it. Or we could also say that pi times the integral from 0 to k of the square root of x squared dx is equal to pi times the integral from k to 4 of the square root of x squared dx. So again, we can either take half that volume we found and set it equal to the integral from 0 to k, or we could say, hey, going from 0 to k and from k to 4 is the same thing. So hopefully you guys are cool with that. We made it through our last video. We're going to do tons of practice in class with these AP questions and make sure you guys are good and make sure you're ready for your test. I will see you guys later. Bye.